Welcome to Calculus. Today we will investigate finding limits of difference quotients, focusing on how that task compares to finding limits of average rates of change. Let's take a look at two examples to add to the two examples we'd seen on our previous segment. I'm going to head over to my notes screen. So our first example for this find limits of difference quotients is here. And what we should do initially is try to compare what taking a limit of an average rate of change is with regard to finding the limit of this difference quotient. So just to review for a moment, the limit of an average rate of change we had defined kind of as going from the slopes of secant lines to the slope of the tangent line on a graph. So let's record that here just so we have it in view. So it's a limit of average rates of change. And let's give that expression. So the limit as x approaches c of, so it really followed the idea of slope. So it was f of x, the y value, minus f at c, which was a value with a constant number plugged in over x minus c. And the way we had set that up on the graph, just to recall, was with some x value out here and some c value over to the right. And what we were looking at was some function. So we had just given a kind of a generic function, not quite sure what its equation is. But what we were claiming was, hey, if I've got an x here, the value there on the y-axis is f of x. And then the value when I trace c over to the y-axis is f at c. And the idea was, let me slightly adjust this so we have more of a curve there. The idea was that this expression gives us some kind of secant line slope. And remember, a secant line is a line that crosses a curve twice. But the claim that we were making is if we take the limit as x gets closer and closer to that c value, which again, it's kind of moving away from being a secant to being a tangent that intersects the line in just one point, that's what we're really doing when we're talking about the limit of the average rate of change. Let's see how the limit of a difference quotient, how that compares to that limit of average rate of change. So we'll just write it here to the side. So the limit of the difference quotient, again, what we'll do is we'll start with a graph just to distinguish these two expressions from one another. So I'm going to sketch again this generic curve. Some function. And then I'm going to mark again on the x-axis 2 spots, but I'm going to do it differently. So here to the left, I'm going to say that this is a point x. And then instead of setting another point out to the right and calling it some other variable, I'm just going to say that the distance between those two x values is h. So if I think about what the coordinate would be for this x value on the x-axis in red, that would be x plus h. Because I'm taking that x value and I'm adding to it the distance between itself and that second point. Again, if I trace over to the y-axis, that's f of x plus h. Because to get the y value, I would just plug in whatever x plus h is into the function. And similarly for x, that's f of x. So we can rewrite that same idea. It is delta y over delta x. And again, what we're doing there is we're saying this is the slope of the secant line that crosses the function at those 2 points. So the slope of that would be f of x plus h minus f of x. So notice how it's forming this numerator just like we're seeing down here in the example, and that's all over x plus h in parentheses minus x. Then what we need to note is that in the denominator there, I've got an x positive in the red, negative in the green. So those end up canceling each other algebraically, and we get this statement. So it's f of x plus h minus f of x all over just h. So again, what that describes is the slope of the secant line, the line that crosses our function at 2 points. Where we're headed in calculus is what's the slope of the tangent line, and that really forms the basis for our idea of the derivative. So the idea is if I take the limit of this difference quotient as h goes to 0, so let me write that out front, the limit as h, so again, h is the distance between my 2 points on the x-axis. As that distance gets smaller and smaller and smaller, where we're headed, finally where h equals 0 is that tangent line. And again, that's what we're after in terms of where we're headed in calculus. So very related, the limit of the average rate of change, the limit of the difference quotient, it's really just, in one case, in the green here, we're looking at 2 defined points. One is c, one is x. Over here on the difference quotient, we're looking at x, and then the other points defined as being h away from x. So the difference quotient is more distance oriented, whereas the average rate of change is more 2 distinct points oriented. Well, let's put it into action. So I've got this instructions to find the limit of the difference quotient for this function f. And then I have that same expression that we just wrote, the limit as h approaches 0 of the fraction f of x plus h minus f of x all over h. So I'm going to set the limit up. The limit as h approaches 0. And when I get to this first term in the numerator, f of x plus h, what I'm going to do is I'm going to substitute anytime I see x with the sum x plus h. So the way that that'll look is it's 2 times parentheses x plus h squared plus x plus h. And then I'm going to subtract from that simply the original. So minus 2x squared plus x, because that piece is just f of x. For my denominator, the nice thing with this version is that it's just h. So now I need to simplify that numerator. There's a lot going on there, and I'm going to start here with that x plus h squared. So this equals the limit as h approaches 0. So as I FOIL this out, I'm really going to multiply x plus h times x plus h. I'm going to expand it here on the right. So my first term's going to give me x times x is x squared. Outer term's x times h, so that I would write that as hx. inner terms, let me mark these arrows. Inner terms, h times x as well. So those two will combine, and then h times h is h squared. So this all has the value of x squared plus 2hx plus h squared. Now that I got to put in here in my numerator. So this is now 2 times that x plus h squared, which is x squared plus 2hx plus h squared, plus x plus h. So at this point, I can leave that out of parentheses. And then over here, I need to distribute this negative. So we're kind of picking up the simplifying as we encounter it. So that's negative 2x squared minus x. Still all over h. So we got to keep going. I need to keep simplifying that numerator. So that's the limit as h approaches 0. Distribute this through. The 2 is going to each one of these three terms. So that becomes 2x squared plus 2 times 2hx is 4hx plus 2h squared plus x plus h minus 2x squared minus x. And that's all over h. Now, at this point, I'm ready to cancel really 0 pairs in my numerator, items that are the same value, but one's positive, one's negative. So I do see I got a 2x squared positive and negative. Those cancel by subtraction. I also have positive x, negative x. And then with what's left, let me circle those in the green. I got these three terms. They're all positive terms. I'm going to divide out an h. So I see that this 4hx has an h, 2h squared has h times h, and h is itself. So the way that's going to look is it's canceling with this lower denominator of h. So that goes, and it cancels one of these in each term. So as I write my next simplification of the limit expression, all I've got left in the numerator now is 4x plus 2h plus 1. And the denominator has canceled out. So now at this point, what I'd like to do is just by direct substitution, take that limit. So notice that the way the limit's set up, I'm really just considering h. I'm not really thinking about the behavior of x. So h is approaching 0, so the direct substitution will be 4x plus 2. Instead of h, I'm going to substitute in 0 plus 1. So out of those three terms, the one that's canceling is this product of 2 times 0. And our value for this difference quotient limit as h approaches 0 is 4x plus 1. And that completes that process. Let's take a look at one final example here. So here, our previous example, our function was a quadratic. It was a x squared function. Here what we've got is a rational function, so 2 over x. So what I'm going to do is, again, follow those same guiding principles as I write this different quotient. So it is the limit as h approaches 0 of the function. So again, remember, I'm substituting in x plus h at the outset for that first version of f of x. It's f of x plus h. So this is going to be 2 over x plus h. And then my minus f of x is going to be minus 2 over the original just x. And then down in the denominator, h. So it's a little simpler, at least from the preliminary view of it. we do have fractions and fractions, so we got to simplify our complex fraction to begin here. So let's set out to do that. So this equals the limit as h approaches 0. So I need those denominators the same. I got them as x plus h and x. So I know that the common denominator is going to be x times x plus h. So I'm going to put the 2 up here, and I'm going to multiply it by what was different. So I would have multiplied by this x, because we already had an x plus h. Minus, and again, I had an x there. The new part in the second fraction is x plus h. So in my numerator, I'm going to have 2 times, in parentheses, x plus h. And still, that's all over h. So now my denominators are the same in the numerator, so I can combine those two fractions by subtraction. So my next limit statement is going to be that it equals the limit as h approaches 0. And I'm going to bring those two fractions together. Their common denominator is x plus times x plus h. Got it. And in the numerator, it's going to just be the first numerator, 2x, minus the second numerator, 2 times x plus h, all over h. For my next step, I want to simplify this numerator, see if I can cancel some stuff. So my next limit expression is limit as h approaches 0 of 2x minus 2x minus 2h, if I distribute that minus 2 through the parentheses, over x times x plus h over h. So I'm looking in the numerator of the numerator, and I've got 2x minus 2x, that cancels. So my next step, what I'm really up to here is I want to multiply by 1 over h below and by 1 over h above to cancel this denominator, get everything in one fraction. So that cancels. H times 1 over h is just 1. So for my next expression, it's going to be limit as h approaches 0 of negative 2h times 1 is just negative 2h over x times x plus h. And then I'll just put it in red so you see how it's entering this fraction, times h. At this time, what I can do is cancel some of these h terms. So I got a 2h above and an h factor below. So h divided by h cancels out. That's just equivalent to 1. And this is very close to being complete. At this time, what I got is the limit as h approaches 0 of negative 2 over x times x plus h. And now I'm ready for the direct substitution. I can put in 0 for h. And again, I'm not going to touch the x's because the limit is in terms of h only. So this has the value of negative 2 over x times x plus 0. And then x plus 0 would just reduce to x. X times x is x squared. So a final answer here, in fact, we'll bump down this direction, is negative 2 over x squared. And that completes that second example. Thank you for joining for this second installment of examples for calculating the limits of average rates of change, as well as the limits of difference quotients. Thanks for joining. See you soon.